Hi everyone, this video looks at material categories and behaviour, which is part of the materials topic for A-level physics. We will look at crystalline, amorphous and polymeric materials and how their behaviour relates to their atomic or molecular structure. If you want to get the free presentation and question sheet for this topic, along with lots of other resources, click on the link in the description below. Enjoy the video. This video is about material types and material behaviour. Just double check with your specification because not all A-level exam boards need this level of detail. But there are three categories. There's crystalline, amorphous and polymeric. And we'll look at all of these in detail, and we'll also look at the behaviour and explain how that is related to their atomic or molecular structure. So let's get stuck in. There's a lot of content in this. This would very much lend itself to a longer response question in the A-level exam, and you might get one of these questions where there's a blank page and you have to write lots and lots of information. So lots of detail. There's no calculations in this particular part. So let's have a look. Crystalline. So we have, you've probably seen this kind of thing before at GCSE. So we have a regular array. So there's long range order. So we're looking at ice and diamond and salt crystals and metals, and we've got this regular structure. However, if we have something called a polycrystalline or crystalline, then you don't have this repeated pattern all the way through. We have grains. So you might have this kind of arrangement shown here. So within the grain, then all of this will be regular, but then you have other grains which are aligned at slightly different angles. So there's a bit more complexity there. So we've got metals, ionic minerals. So if you've done GCSE chemistry, if you're doing A-level chemistry, then you'll know a lot more about this. Okay, so we might get asked to have a brief description of what's meant by crystalline and maybe some examples. So metals, ionic materials would be an easy one. So we'll revisit this one later on in the video. The next category is amorphous. So the key thing here is there is no regular order. So we can see here this is very different from the previous screen. So we have this random arrangement of atoms and we get these kind of clusters together. So it's varied and it's not continued in a long range. So this would include glass, so various types of glass, ceramics and also brick. So again, we've got a very brief description of what is meant by amorphous and then one or two examples. The next category is polymeric. So I'm sure you've come across this before. So this is polymers. So poly means many, meric I think means molecule, I might need to check, but we have long chain-like molecules. So we have some kind of molecular structure, which we do not need to know about. This is very much chemistry. And then it's repeated over a long chain. So we have this repeated pattern. So we need to have that brief description and then some examples, so rubber, wool, and then various synthetic materials like nylon and polythene. Okay, so you could get a question which is just 3 marks, state the three categories as described in the A-level specification and give an example of each. So if you get a question like that, that will be nice and straightforward. So let's have a look at a bit more detail. So crystalline solids. Now this is very much related to what we've done already in the materials topic. So this is ideas of elastic and elastic limit and plastic, but we probably need a bit more detail. And in fact, very often, as we probably said earlier on in the course, we just simplify this situation for the behavior of a ductile material, a crystalline solid, just to a straight line section and then a curved plastic section. But in actual fact, there's a bit more going on here, and this can be drawn in various ways. So I've drawn it in this particular way here. So just to go through all the different stages here, and you could get a question again, a 6-mark question, describe in detail what's going on or label the points or the sections and explain what's happening. So we could say right at the start, the stress and strain are proportional, so it obeys Hooke's law. So we know what Hooke's law is. Stress is proportional to strain, or force is proportional to extension. And then we have the limit of proportionality. So P is the point beyond which the relationship is no longer a straight line through the origin. So there's a bit of curve here. However, it's below the elastic limit. So even though there's this little curved section here, if we take the load off, it will still go back to its original length, which is the definition of elastic behavior. So if we go a little bit beyond P, we go up to E, this is the elastic limit. So we've mentioned this before. So beyond this point, then if you remove the load, it will not go back to its original length. We will have permanent deformation and we have plastic behavior. So we have the distinction between elastic behavior to the left of this massive line. This would all be elastic, and then to the right will be plastic behavior. Okay, then we also have the yield point. Okay, so we don't need to know why we have this. We just need to be able to recognize this as a separate point on the stress strain graph. So if we go beyond here, then a relatively small increase in the load or the stress will cause a very large extension. So this is why we have this very long line or curve to the right of this point. And this is what we understand by ductile behavior, and we'll talk a bit more about this on the next slide. And then our final point on here is the breaking stress, and this is the point at which the material will actually snap, and that is the kind of the end of this relationship on the stress strain graph. Right, so a bit more detail. You might be asked, well, why do we have these different sections? So this is to do with edge dislocations, as we will see. Before we get into that, we can just talk about if we are below the elastic limit, then we have this, the force between the atoms is proportional. If we increase the separation, then the force is proportional to that. And again, we don't need to know about that in detail, but we do need to know that there's a force literally holding the atoms together, and if we apply a force, then it will stretch. If we remove the force, then it will go back to its original length. So that is our elastic behavior, and that's also our Hooke's law relationship. But this idea of edge dislocations, this is really important, and we will talk about what these are, but even if you just write that word, you should get a mark for that. So we have this imperfection in our long range array of repeated pattern. It's not quite perfect. And this is just the way that metal crystals or crystals form. So we have this, this line of atoms comes to an end here. So this is what we mean here by the edge dislocation. So what's the significance of that? So if we apply a force here to the left and to the right, and we go beyond the elastic limit, so we go into the plastic region, then these bonds will try to break. So maybe the bond here will break and then reform with the one to the left, and then this will shift along. So these bonds will kind of break and reform. So what we had on this line here has now moved along. It's quite difficult to do with a static screen. I do have a nice PowerPoint of this, which should be in the free resources on the PayHip site. But what we end up is we have this movement of bonds from the right to the left, and we end up with a permanent extension. So we're actually breaking and reforming atomic bonds, and as a result of this, we stretch out the material. So we end up with a permanent extension. Okay, so this is why we have elastic behavior below the elastic limit, force is proportional to extension, and plastic behavior above the elastic limit, because we're having these bonds breaking and reforming to give us a permanent deformation. Now this may be problematic, so we can actually reduce this effect. So if I add impurities, so as different materials, so we've got a carbon, for example, this can prevent this happening, because we add more atoms into the structure, and it prevents or reduces this mechanism of breaking and reforming the bonds. So that might be something you need to know about. The final thing we're going to mention here is this idea of necking. So what we end up, if you've probably seen something like this, and you can, if you Google, if you look for a video on YouTube or Google, you should be able to see this actually taking place. So there will be a failure point where the material gets thinner and the diameter reduces. And why this happens is because we get this reduced, well, we get an area and we'll get some imperfection here, which causes the area to be slightly smaller. And because the area is smaller with the same force acting through, then the stress will be greater. and then we end up with the fracture point at that point because of the greater stress. Right, so again, lots of information here. This would lend itself to a 6-mark question, and a lot of this is to do with the correct terminology. So edge dislocations, necking, and adding impurities. So we're going to look at why we have this behaviour with amorphous, or what's going on here. Very, very different. So we have our stress-strain relationship. It is a straight line, so it obeys Hooke's law. Up to the elastic limit, but the key thing about amorphous materials is there is no plastic region. So if you think about the behaviour of glass or ceramics, if you hit a piece of glass or ceramic with a hammer, it won't end up taking on that shape. You won't be able to change the shape of it. It will just shatter. Now there is a very small amount of elastic strain, but at that elastic limit, that is the breaking point. So there is no extra section here. So that is very, very different. We have brittle behaviour in amorphous materials as opposed to a ductile behaviour in crystalline solids. So we can talk about how amorphous materials break. So you'll have very slight imperfections along the top or on the surface of the material. So they have these tiny little microscopic cracks. So when we have a tension applied, then if you imagine this little crack here and look at the tip, then the stress at the tip of the crack is going to be higher, and that causes the crack to propagate. So you're probably familiar with glass shattering, and we're getting these particular shattered edges in ceramics and maybe with ice as well. And this is what's happening here. So we're getting this focusing of the force on a very small area. So we get a high stress, which will find its way through the material, and then this is what we understand to cause the failure. This is brittle fracture. So there are 2 ways we can strengthen amorphous materials and reduce this brittle fracture. So one thing we can do is reduce the number of cracks on the surface. So when it's being manufactured, whatever product it is, we can take real care that the surface, the edge, is as smooth as possible, so we have as few of these cracks as possible, which will reduce this mechanism taking place. Another thing we can consider is if I just have a cross-section rectangle shape here and I apply a load to the top, then it's going to bend slightly. If it bends slightly, then we're going to increase the tension in the lower section and the compression in the higher section. And that tension, if this bottom section is stretched, then that's going to increase this likelihood of cracks producing brittle fracture. So one thing we can do is use a pre-stressed concrete. So if you're producing a large concrete beam, so we can put steel cables through, which will strengthen it anyway, but we also add a bit of curvature as well. So we have this kind of situation here, so it wouldn't be visibly curved that much, but there's a slight curve by applying different tension to different cables, so that when a load force is applied, then that actually pushes it into a flat horizontal shape like this. So under load, we have this rectangular cross-section rather than a curvature, which means we're less likely to get cracks on the lower surface. Right, the final thing we need to consider, the final material, is polymeric, and we did look at this in a bit of detail earlier on in the course. So various things about polymeric materials. First of all, we have this what's called an S-shaped curve. So it does not obey Hooke's law over the range of the loading, but we could say right down here, if for small forces, then it's approximately linear. So we could say it obeys Hooke's law for low loading or small forces. And we know that, we've said already, that polymeric means long chains of atoms all tangled together. So initially, when we're untangling them, then that requires a large force because we have lots of attractive forces between these long chains of atoms. So it's quite difficult to stretch it to start with. So we have a steep gradient here. That means a large spring constant, which means it's difficult to stretch, it's stiff. So we have this midsection here which flattens out a little bit. We've got a lower gradient, which means a lower stiffness or a lower spring constant at this point. Because at this point, we're just unraveling the chains or straightening the chains. That's relatively easy to do, so we have a lower gradient. And then we have the chains fully extended, and that's quite difficult. We're stretching the chains themselves. This requires more force, so once again we have a steeper gradient. So we have difficult to stretch, easy to stretch, and then difficult to stretch. And we end up with this particular curve, which is referred to as an S-shaped curve, which probably does not look like an S, but that's what it's called. We've also studied before that the area underneath a force extension graph represents the work done or the energy stored. And we can see that if I was to work out the area underneath the loading curve, that's significantly larger than the area underneath the unloading curve. So there's a difference between those two energies. So the work that I put in, I do not get all of that back. I get a little bit of that back because the mass will rise if we're stretching a rubber band. So that will convert to GPE, gravitational potential energy. But all this area inside, which I'll try to colour in now, we lose that energy, or even better, that energy is converted to heat. So this is referred to as hysteresis. You may or may not need to know that term, but that goes into heating up the material, and we do not get that back for this particular set of load conditions. Right, so that's a lot of material, a lot of, if you pardon the pun, that was unintentional, a lot of content, a lot of information, and you will have to practice writing this out in detail, especially for those long response 6-mark questions. So well done for getting through that video and for reaching the end of the materials tutorial videos. So you could have a look at the materials playlist if you haven't done so already, and there's lots of other playlists and lots of other information on YouTube. If you want more structure and more detail, then go to payhip.com, grade A physics, and we have structured courses, lots of questions, lots of exam questions, work solutions, some really good recap quizzes and progress tracking. So check that out if you haven't found that already. See you next time.